So again, calorimetry is a pretty common technique done within AP Chemistry and in Chem 1 for that matter when it's dealing with heat exchange. So we have to remind you of everything that works with that. What I'd say with this is the AP questions will often have procedural things. I don't know of any AP class anywhere that doesn't do titrations. I mean, that's just kind of a must within AP Chem. You did some in the first unit, you're going to do a lot more in the second semester as well. Spectrophotometry, on the other hand, is not done everywhere because the machine is expensive. And we kind of luck out here that we have a reasonable budget to get those machines. I actually bought one to replace one that wasn't working well last year. But not every district can do that. And one of the things the College Board has to be concerned about is writing a test that puts, quote unquote, the rich school districts at an advantage over the poor school districts. So they don't always ask questions dealing with spectrophotometry. Calorimetry is styrofoam cups usually. Every district can afford that type of equipment, so that is a more likely laboratory question. I have students that are in Physics 2 that say, well, in Physics 2 we have these fancy calorimeters that are a little bit nicer, and I could use them if I ever wanted to. Rodemacher says I can. Yeah, I know that, but the questions that you are going to see typically on an AP test are dealing more with the styrofoam ones, these simple ones that any district can afford. So that's why we stick with that when we refer to calorimetry. So first off, why do we do it? We're measuring that exchange of heat. A calorimeter is ideally a closed container that won't allow any interference of the heat exchange from one thing to another. However, we use the styrofoam cup. Although, again, we are well off to do school districts, so we use 2 styrofoam cups, ladies and gentlemen. We double them up. That really makes a difference. I even make lids for them as well. So in Chem 1, we don't let the Chem 1 students use lids. But I make lids. I think Soph even saw me making some of the lids yesterday. Because unfortunately, my long-term sub last year, after they were doing a lab, they threw out styrofoam cups. That's bad for 2 reasons. One, the styrofoam doesn't biodegrade, so you're just putting it in a landfill. Secondly, that's my equipment that I need to use. You don't think of it as a nice piece of equipment, but heck, I can use that year after year. And then the new styrofoam cups that she bought to replace that were a little bit smaller, so I had to make new lids on some of these. It's really fancy stuff. Do I have anything else on this slide? No, I don't, so let's go back here and make sure everyone's got this. So again, we use the styrofoam cups in Chem 1 as an insulated material. We will be doing that again. Ideally, only the stuff inside the cup is exchanging heat, nothing else is involved in this. But just like the lab that you turned in, I had you talk about sources of air. Usually with calorimetry, there is going to be sources of air. That there's a reason why the heat doesn't change as much as it should, because our calorimeters aren't perfect. But that lends itself right into those AP questions that you could see as well. A couple of terms are specific heat capacity and heat capacity. Our textbook labels specific heat capacity as C sub S. On the AP equation sheet, they just call it lowercase c. This is defined as the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Now our textbook probably gives common values for that. I would actually delete this right here because I think this notes is based off of last year's textbook. So I'm actually just going to do that right now. But yeah, these are known values. Water, for example, 4.184 joules per gram degree Celsius. That means I need 4.184 joules of energy to make 1 gram of water increase its temperature by 1 degree Celsius. If you don't recall from Chem 1, water is something that's considered to have a fairly high heat capacity. It takes a lot of energy to make water change its temperature. One of the reasons why our body is primarily water. It helps us maintain our body temperature. Because if we don't, protein synthesis then is affected. Something that's less commonly used is uppercase C, which is referring to heat capacity. That is the heat required to raise the temperature of a substance by 1 degree Celsius. It's not based upon the mass of the substance at all. It is a lower point of emphasis, however, it is sometimes used, so I want you to be aware of that term instead. Especially for those Physics 2 students, their type of calorimeter takes into account this uppercase C a little bit more than what we would with our styrofoam calorimeters. The next slide is going to go over a couple of equations that we will be using here and there. Okay, looks like we're ready. The first one, that uppercase C equals the mass, which is M, times the specific heat capacity. Again, M stands for mass. This is not the most common equation that we will use. The most common equation that we use is Q equals MC delta T. That's why I put this one in bold. This one is actually given to us on our equation sheet. So this is kind of the calorimetry equation. If you see any, like when you see an uniometer, you should be thinking partial pressure. When you see styrofoam cup calorimetry, you should be thinking Q equals MC delta T is used at some point in that process. Again, M stands for mass, C is that lowercase c, that specific heat capacity. Delta T, again, triangle is delta. Come on, no more Greek here, ladies and gentlemen. Walk down Langdon Street, learn that a little bit, Madison. Delta means change. Final minus initial temperature. I don't think you need to actually write down this next, this equation here, all I'm doing is substituting the lowercase mc for the capital C. Again, it's typically not the equation that you're given. Most of the equations that we work with are just going to be Q equals MC delta T. However, our textbook does bring up the other one instead. Yeah. Heat. Sorry. T's temperature. Temperature, yeah. So lowercase t time, uppercase T temperature. We will actually be doing stuff with time next semester. So yeah, we do have to know our uppercase from our lowercase. Remember the equation sheet that AP gives you on the left-hand side gives you the equations, and the right-hand side they actually define all the variables. So they would have to make sure to then tell you that part. What I meant to say was this last problem on the bottom, I don't think you need to write down. This would be about as simple of a problem as we could give you though. Where if I give you the mass of something, 869 grams, I give you how the temperature changes from 94 to 5. Well, that means the 5 is going to be the final, 94 is the initial, and it gives you the C value, or some textbooks call it the S value. You could solve for that answer then, where it'd be a negative value because the change of temperature lost heat, and then multiplying it out using Q equals MC delta T, I could get negative 34 kilojoules. In other words, when I first solved that, it'd probably give me negative 34,000 joules. I just convert to kilojoules afterwards. It's very common with the big numbers to use the metric system to our advantage. So this would be a very cut and dry problem. Hey, here's the mass, here's the change in temperature, here's the C value. How much heat was either taken in or given off? By the way, since this is a negative value, is heat taken in or is it given off? Is this endothermic or exothermic? Exothermic. Negative values represent heat is being released. So we have to keep in mind those types of things as well. Again, what we have to do with our calorimeters, there are two different types of calorimeters, and a constant volume one, which is often referred to as a bomb calorimeter. That's the one that has to use the capital C in its calculations, because you will know not only the amount of heat that like the water absorbs in the response, but you also know the heat that the calorimeter itself absorbs. We use a constant pressure calorimeter. And what we do is really this last bullet point. The entire point of the math that we do is if we can find out how much heat was either gained or lost by one thing, conservation of energy says the other thing involved in that reaction or process is what did the exact opposite. And ideally, no heat is lost to the surroundings or gained from the surroundings. Remember those terms, system and surroundings, from last class? Perhaps that's not always the case, but it typically works out pretty well with our calorimeter. So not a lot of notes I wanted to give you today because I wanted more today to be about us doing stuff in the lab to remind you of Chem 1, and then I do want to go over a little bit of math at the end of the hour, also dealing with phase changes, which is stuff that we did in Chem 1 also. So once you have this jotted down, so looking at this phase change diagram, if you don't recall this from Chem 1, a solid is the first slope, a liquid is the second slope, and a gas is the third slope. Again, if the y-axis is temperature, you can see temperature of a solid can increase. However, there are plateaus, and that's where a phase change occurs. That phase change then requires energy without its temperature changing. Then a liquid, then the same with the gas as well. What we went over in Chem 1 is the steps in order to do a problem like this. And actually, how about we do question number 2 on this worksheet? Question number 2 says, if 62 grams of steam at 122 degrees Celsius is cooled to 2 degrees Celsius, how much energy is needed or released? What we typically told students is to use this phase change diagram to their advantage, where I would say that this temperature is 122. Why am I saying that? Because it has to be a gas if it's 122 for water. And this plateau right here is occurring at 100 degrees Celsius, that boiling point of water. And it goes down to 2 degrees Celsius right here. Maybe I'll put a label on it. So if we were doing a problem like this, we have to figure out how much energy change occurs going from 122 to 100. Then the condensing of that liquid from here to here. So this would be step 2. Finally, step 3 is going from liquid water at 100 degrees Celsius to 2 degrees Celsius. This looks a little bit familiar from Chem 1. Again, I don't know what your thoughts are. I'm just trying to figure this stuff out. Okay. Anytime you have a temperature change, whether it's a solid, liquid, or gas, Q equals MC delta T. The mass in question number 2 is given to us, 62 grams. In order to solve a problem like this, they'd have to give you the C value. The heat capacity of a substance varies based upon its state of matter. Water, you know, 4.184. That's liquid water. I would have to give you the C value for the gas here, which that C value is 1.99 joules per gram degree Celsius. Delta T is final minus initial. The initial temperature in this problem is 122. I have to solve for it going to 100. So that's a negative 22 degrees. Negative 2,700. Does that sound right for those of you who typed that in? I'm going to keep all the digits, but one of the things I'm doing is I'm just marking down the second sig dig. That way I know that's where I should have rounded it to. There's step number 1. Good. There is no temperature change during a phase change. Either energy put in, or in this case, energy released. In this particular problem, going from a gas to a liquid, that energy being released is allowing the molecules to align to attract one another. The difference between a gas and a liquid is that attractive force. My step number 2, to solve for heat, which is Q, can be written a couple different ways. It could be the mass times the heat of vaporization. That's probably the most common way that you'd see this written. I'm going to extend this up so I don't have to bend down as much. Heat of vaporization. There is 2 different ways that this could be shown to you. Typically, in AP Chem, it would give you a value like 40.79 kilojoules per mole. Reporting heat of vaporizations and heat of fusions in kilojoules per mole is the most common way that it's done. In Chem 1, you never had that. Because in Chem 1, what I did is I converted it out of moles for you. I converted it out of kilojoules for you. And I'm actually looking at a Chem 1 copy of this. I gave you that value as 2,263 joules per gram. It depends on the unit in which this value is given to you to decide how you would go about solving it. In AP Chemistry, however, it is more common to be given the kilojoules per mole value. It's not working. Just trying to separate out my work here now. I'm getting all over the place. It is more common to give you the kilojoules per mole part. So if I did give you 40.79 kilojoules per mole, for example, what I'd have to do is take my 62 grams and convert it into moles. 1 mole over 18.02. Then I can multiply it by my heat of vaporization, 40.79. However, I'm going to report that value as a negative 40.79. Sorry that I'm getting all vertical here. I'm reporting it as a negative 40.79 because heat is being released during this process instead. I'd get negative 140 kilojoules from that step. Finally, step 3, if I go way back up here, is going from water at 100 degrees Celsius to 2 degrees Celsius. And back to Q equals MC delta T. Mass is 62 grams. The C value of liquid water is the one that you should know, 4.184. Negative 98 degrees Celsius. Oops. Once you get the amount of energy of all 3 steps, you can add up those energies. However, make sure they are in a similar unit. So, for example, I have kilojoules in the middle step, and I have joules in the other 2. Let's make sure to convert those over so they all have a similar unit at that point instead. Now I'm actually looking at a Chem 1 worksheet where I did all that conversion for you. So the C value of ice, this helps you out for question number 1, is 2.03 joules per gram degree Celsius. And the C of water is 4.184 joules per gram degree Celsius. C of steam, which I just covered, is 1.99 joules per gram degree Celsius. Heat of vaporization I already showed you, but typically it's 40.79. The heat of fusion, which would be the solid to liquid phase state. Boy, I'm having a hard time remembering that off the top of my head in joules or kilojoules per mole. For some reason I'm thinking like the 6.01, but I have 334 joules per gram written on that one. And I will look that up quick, but I think it's 6.01 is the number that rings in my head. In fact, we could solve for it if we really wanted to. But what I think would be a good thing to do is you could do question number 1 as a practice problem. Actually, 3 and 4 on the sheet don't actually have to deal with the phase change aspect of it. But then at least you'd have a little bit of practice in something that we did back in Chem 1. And that's all that I wanted to wrap up class with today, was reminding you of what we did there. So it's another day that we might get done a smidge early, but things like putting away graduate cylinders and scales and stuff like that could still be done to wrap up class too.